in the starting material.
Yeah, but if the O is the nucleophile, a neutral O only goes for ethanol.
Yeah, that's what I didn't notice that at the start. That's bothering me too. So normally neutral oxygens are not good enough for SN2. So I actually I didn't know that this reaction would work here, but you have it in your notes, so I guess this actually works. In this case, we have a really good leading group over here, and we've got a lot of this methanol over here to react with itself. So I guess this is an exception where you can actually use a neutral oxygen as a nucleophile. Actually, I didn't know about this exception myself already, but you have this in your notes, so I guess we'll have to treat this as an exception where we can actually use this for an SN2. It definitely can't be SN1 because you can't form a primary carbocation. Let's try drawing the arrows for that. All right, so we know that this arrow means this oxygen is using the pair of electrons to form a new bond to this carbon over here. Maybe I'll number the carbons. 1, 2, 3, and 4. So over here, this oxygen is going to be bonded to our number 4 carbon, which also has this CH2, and the number 4 carbon is bonded to the number 3 carbon. Right. Remember, these are not IUPAC numbers, they're just reference numbers. And then we're also going to have the water leaving group. All right, so it looked like most of you got the right bonds right, but it looks like a couple of you got the most important part wrong, which was the charges. Remember, the charges are the most important part. Every time you do every step, you have to change the charge at the initial tail and the final head. So who's at the initial tail? Here's our initial tail over here. Now, this oxygen started neutral, and it is losing electrons, so it's going to end up positive over here. Okay, and then this water started positive, so it's going to end up neutral. Okay, so that would give us this at this point. Okay, so the charge really is quite important here. By the way, this is now, I'm sorry, so this gives us this so far, and I think someone already mentioned what would happen next.
Deprotonate.
Yeah, a deprotonation step. So our last step is, I think we've already seen a bunch of examples like that. Who can we use to deprotonate this?
The bromine.
Remember, this was supposed to be catalytic. So since we used up the acid in the first step, it would be nice to get the acid back at the end over here. So we can use this bromide.
I'm not using it. In the example, they use the starting material again, because we're trying to make the symmetrical ether.
So the point they're making is that the reaction could continue there. So we can come back to that. So all right, so using our deprotonation here, we've deprotonated this oxygen. That would get it back to neutral, and that would regenerate our catalyst over here. But then, now that we've regenerated this catalyst, we could do the whole thing all over again. The catalyst could protonate a new alcohol molecule, and that could get attacked by another alcohol and make another of this molecule over here. By the way, this is not an alcohol anymore. You know what this functional group is? An oxygen attached to 2 carbon chains. That's an ether. Is that a term you guys have heard?
Yes.
So an oxygen with a hydrogen is an alcohol, but an oxygen attached to 2 carbon chains is an ether. So this is called an ether synthesis. This is a way to make an ether. All right, so one way you can think about this again is then this acid will protonate another alcohol, which will go through another of these reactions, and we'll get another ether. On the other hand, though, instead, you can kind of cut that short. Instead of saying that you're going to go through the acid, you could just say that this guy over here will protonate another alcohol, and then that will, that'll take us through that again. So either of those would be a legitimate way to draw that. You could say that you reform the acid, and then the acid protonates a new alcohol. Or you could say that the alcohol gets protonated from this ether over here. Either of those would be legitimate, if you see what I'm saying. Okay.
So all these reactions have like a clear path that they're going to take, basically. So we kind of just need to figure out, like, if we knew what an ether was, I think we totally would have been able to come up with that product, right?
If you knew what an ether is.
I didn't know what an ether was. I didn't know
right.
that we were trying to make it.
Now, in a way, I guess I would kind of disagree with you for a second. I would say, you should be able to get this right even if you've never heard the word ether. Again, it's not about the molecules so much as asking what is it reasonable for these functional groups to do. For example, you should say, aha, we got a strong acid. Well, I know what's going to happen first. Someone's going to protonate. And then you should focus on where the charges are. You should say, gee, it's really interesting that I have this positive charge here. What does this positive charge do? It makes this a good leaving group. And then you should ask, are there any nucleophiles around? And again, I was kind of surprised to use this example because I didn't know that you could use a neutral oxygen for an SN2 in this case. But anyway, that's what he did. So he used this nucleophile to attack this alpha carbon with this good leaving group. So the key thing is, again, focus on, well, one thing is to focus on the charges. That's the interesting part of the molecule. And again, it shouldn't really matter whether you've ever actually seen an ether made before or not. Remember, on the test, he might give you a totally new molecule you've never seen before, and you're supposed to apply the principles from the class. So one principle is, again, be on the lookout for strong acids and bases. So to summarize the key ideas here, if you see a strong acid, protonate somebody. If you see a strong base, well, it might be a nucleophile, but probably you should deprotonate somebody. And now we've got a new thing you can do with an alcohol. So does an alcohol start with a good leaving group?
No.
No, an alcohol does not start with a good leaving group because it starts with a neutral oxygen. But can you modify the alcohol so it does have a good leaving group?
Yes.
Yeah. What would you do to make it into a good leaving group?
Protonate or deprotonate.
Which one would make it a good leaving group?
The leaving group.
Protonate. So you'd protonate it.
No, you deprotonate.
No, you protonate it.
Does everyone know what the difference between protonating and deprotonating is? So let's see here.
He said it.
It's protonating.
Is this a protonation or a deprotonation?
Protonation.
All right. And this is a deprotonation.
That would make the leaving group. I mean, that would make a nucleophile.
That's right.
You want to
Good.
get a positive nucleophile.
No, you want to get
A
a
good
positive
positive
leaving group.
leaving group, sorry.
But the bottom one is a good
Good nucleophile. So
Right.
that would be a good nucleophile at the top would be good. Okay.
We're getting it. Okay. So a protonation, what does the protonation do? It gives us a good what?
Leaving group.
Yeah, a protonating, and this is not just for alcohols. Protonating things is a way to make them into good leaving groups. Because what is a proton? This is a proton. Anytime you protonate something, it's going to get one step more positive. Anytime you protonate something, it's going to get one step more positive, and we should know positive things tend to be good leaving groups. So protonating anything makes a good leaving group. Alcohols don't start with good leaving groups, but if you protonate them, then you do have a good leaving group. And then you should look to do, say, a substitution or elimination reaction. So protonating it gives us a good leaving group. Good. Now, when you guys are ready, what type of nucleophile is this? Is this a good enough nucleophile for an SN2? Well, usually not. We just used it for one, but usually it's not that good for SN2. Usually it's just good enough for SN1. But is there something we could do to make this an even better nucleophile?
Deprotonate.
Deprotonate it, and now it definitely is a good enough nucleophile for SN2. So the interesting thing about alcohols is that they, in their starting condition, they're not that great at anything. Although even here, this is already pretty good for SN1, good enough for SN1. And we just saw an example where we did it for SN2. Oh, that surprised me. But anyway, here we had this example. But you can make it into an even better nucleophile by deprotonating it. That was what our first example was, wasn't it? So in our first example, didn't we deprotonate this alcohol? And then that made it into a nucleophile that did the intramolecular SN2 reaction. So we can see the interesting thing about alcohols is they can both protonate or deprotonate. They can deprotonate because there's a proton on the oxygen, and they can protonate because the oxygen has a lone pair. Well, if you protonate it, it makes it into a good leaving group. If you deprotonate it, it makes it into a better nucleophile. So those are the things to watch out for with alcohols.
Is it common that you can use the starting materials I know we went back and used the starting materials, but I wouldn't think to do that.
The starting material to react with itself?
Yeah.
Yeah, so that's not too uncommon. So remember that even if you only write it like this doesn't mean just one molecule of starting material.
No.
It means billions of molecules of starting material. So even if some of the starting material, molecules have gone through a reaction already, there will generally still be some unreacted starting materials as well that those can react with. So that's important to watch out for. So the interesting thing here is that alcohols can then react with themselves. We just saw that alcohols can react with themselves. Why? Because we've seen that this oxygen has the potential to act as either a nucleophile or a leaving group. This can be modified to be either a nucleophile or a leaving group, so alcohols can react with themselves. This didn't happen with haloalkanes. There's no way we can modify this. It just is what it is. It has a good leaving group but not a good nucleophile. But we can modify alcohols by protonation and deprotonation to adjust the reaction. So those are the key ideas for alcohols.
Okay.